Welcome to another unit of the ISM course in Statistics 2. In this unit we're going to talk about the normal distribution. The normal distribution is one of the most commonly used distributions in statistics because it also has the advantage that a lot of distributions, binomial distribution, hypergeometric distribution, Poisson distribution, can, for certain properties, be approximated via the normal distribution. That's not the part, however, I want to talk about in this unit. This unit, I generally just want to go about how we can use the normal distribution to calculate probabilities with regard to normally distributed random variables. In this case, we want to start with, well, let's say well-known graph, which is here the so-called bell-shaped or Gaussian bell-shaped curve, which describes the density function of a normally distributed random variable with a mean of mu and a variance of sigma squared. And well, once I have those two informations about my distribution, so the mean and the variance, and I know it's normally distributed, I also get quite a lot of additional information, and that's what this graph actually tells us. It shows us that 68.27% of all observations lie within an interval of mean plus minus 1 standard deviation. Well, standard deviation, the square root of the variance. So once I have the mean and the standard deviation or the variance, I can directly go plus minus 1 times the standard deviation. It's more or less a bit over 2/3 of all observations. If I go plus minus 2 standard deviations, I get roughly more than 95%. So it's 95.45% of all observations. And if I go plus minus 3 standard deviations, I get more than 99.5, so in detail 99.73% of all observations. Why is this so interesting? Well, 2/3 sounds nice, but 95%, with most of the tests we considered, it's usually 5% error. And well, if we here already know plus minus 2 sigma, so 2 standard deviations, it's already a bit more than 95%. So that's a good to-go value for too high, too low values. If you want to make this even more critical, well, with 5% error, we talk about significant deviations. When we have 0.5% error, in some cases we already talk with almost certainty. So plus minus 2 standard deviations means significant deviations, or larger than those two ones means significant deviations. And plus minus 3 standard deviations means we covered almost everything there is. So with almost certainty, the result will lie within plus minus 3 standard deviations. Well, that's a relatively valuable insight to gain. However, we need to assure that the variable actually is normally distributed. Well, our task here is not so much to assure it's normally distributed, we just assume this here, and then continue how this can actually help us with calculating probabilities. For this, I switch to the next slide. Before, however, here we have the function for this. Mathematically speaking, this will not so much be used as what the function and the graph shows us. So if we consider not so much the density function shown mathematically and graphically on the slide before, but the area below the density function, which is here the cumulative density function, which looks like a bit stretched out S. And mathematically, it's more or less the integral over the function we've seen before over the density function. well, it starts at 0, so covering almost nothing, to 1, covering almost everything. And well, the problem with all of this is, would be really nice to just get this function being able to say, okay, I want to have the value for, let's say, z of 1, z of 2, z of whatever. Just insert this given our mean, given our variance, and just calculate the probability. And that's a big problem. We can't. Because the integral given here, well, we can write this down, but we cannot explicitly calculate this, not analytically solve this part here. So we need tables where we actually look up these values. And that's a big problem because, well, we don't want to work with thousands and millions and billions of tables to look up. So we need to use a small trick. The trick is via standardizing a random variable. We're doing this by taking our original variable, subtracting the mean, and dividing the result by the standard deviation. Then we get the so-called standard normal distribution. Standard normal distribution has a mean of 0 and a variance of 1. That's what you usually see when you see the typical figures of this. And the advantage for the standard normal distribution, we can generate tables. That's tables like this. And here, well, we can look up specific values. For example, if you want to have like a value of 0.11, you go 0.1 in the rows, 0.01, that's the second decimal in the columns, and you get a value of 0.5438. So that's easy to go. How will this look like in practical aspects? For this, we have the example here. Imagine we have an x value of 6, a mean of 5, and a standard deviation of 4. Then the corresponding standardized value would be 6 minus 5, that's 1, divided by 4, giving us 1/4 or 0.25. If you look up the corresponding value for the standard normal distribution, we have to look up column, first row 0.2, so the third row, then column 0.05, because the second decimal is 5. Then we end up with a value of 0.5987. Okay, so much for this. That's also how we can use these tables. That's basically here, this value. So what about making our life easier? Because we've seen this table only starts at 0. What if we have negative values? Can we make general implications? Can we deduce some additional properties from what we know about normal distributions and the standard normal distribution in particular? And yes, we can. And the first one is actually, well, if we calculate the probability of x being smaller than different small x, we can just insert this into the function we just had. And we do this by standardizing it and looking up the value in the table for the standard normal distribution. And that's this big phi here, so the large circle with the line in the middle. Okay, that's not so much a rule, that's just how we get the value. But if we take a critical look here at the graph, we see the function is symmetrical. And we can use this because we know the standard normal distribution is symmetrical, but the mean is always situated at 0. So it's symmetrical to the 0. Meaning, if we have to look up a negative value, we can just turn this around and go with 1 minus, and then look up the positive value. Why can we do this? Well, if we consider the mean and look to the left, that's basically the same as if we mirror this and look to the right, because the area to the left equals the area to the right. So the area smaller than, here in this example, for example, mu minus 1 standard deviation, the area left of this, that would be, if I go over here, this area here, is actually equal to the area to the right of mu plus 1 standard deviation, which is here, this area. So it doesn't matter if we go with minus 2 or 1 minus phi of 2. So we will get the same results here. In particular, this means we only need positive values in our table, because every negative value can directly be transformed into a positive value. Okay, this is one property. The second property is that if we want to have an interval, so our random variable should be somewhere between A and B, then we can first calculate the corresponding probability for this being smaller than B, and then subtract the probability of the x being smaller than A. And why can we do this? Well, this means, for example, we go with B. For example, B is here at 1 standard deviation. We calculate the area to the left of this. That's this area. But we want to have this only for this part in between. So we are calculating first all of this area. And then we're calculating the area to the left of this one. And we subtract this from the large part. So we're left with everything that is in between. And well, you've done something similar if you worked with integrals in general. Because in integrals you do the same thing. First, you insert the upper boundary, the upper bound, into your primitive, and then you go minus and insert the lower bound into your primitive. So basically here we see that working with probabilities in this case is not so different than working with integrals. Okay, so this makes working with certain parts a bit easier. We have a second part, which basically means the probability of being different from the mean by a certain amount, which is here C. So for example, the area of being at least 1 sigma away from the mean. In our graph, this was translated into this part here on the right and this part here on the left. So in other words, we can just calculate one of them and then multiply this with 2. So for larger than C looks as follows, and then we can do the same thing for smaller than C. So that's basically 2 ways to make our life a bit easier. Again, if we have similarly far away upper or lower bounds. So telling us should be within an area, second formula, as most so and so far units away, or should be farther away than this and this threshold. That's the first formula. And well, that's already quite a lot of things we can just deduct from this simple graph of the distribution. But how would this work with a practical example? That's what we're going to take a look at here. So we start with the weight of check-in luggage at an airport is normally distributed. On average, a piece weighs 17 kilograms with a standard deviation of 2 kilograms. The threshold lies as 20 kilograms, and above this threshold, an additional fee has to be paid. Our question now, what is the probability that a checked-in piece of luggage weighs more than 20 kilograms? So first off, we note that our mean is 17 kilograms, the standard deviation is 2 kilograms, and we are asked to calculate what is the probability that our random variable x is larger or equal to 20 kilograms. Well, larger or equal, that doesn't work with what we had here with the first formula on the previous slide. So we reformulate this to 1 minus, and then x is smaller or equal to 20. Here two things. First, we can do this as well with the 1 minus, because, well, the whole area below the density function is always 1. That's the maximum probability there is, 100%. And if we split this up into a part smaller than 20 or larger than 20, together they make up the 100%. Okay, but what about the situation that I have equal to 20? We might recall from binomial distribution or hypergeometric distribution, we had to go with greater or equal to, and then 1 minus x being lesser than, not lesser or equal to. Well, here this is no problem because we have a continuous distribution. With continuous distributions, we can only work with the cumulative density function, because one specific probability, so for x being exactly 20, the result would be 0. Well, if you don't believe this, just turn back one slide and take a look at the second formula where I said, well, if you calculate the probability of an interval from A to B. Now imagine this interval to be from A to A. So from the probability of this being smaller than A, you subtract the probability of this being smaller than A. So you end up with 0. So here it doesn't matter if we go with greater than or greater or equal to, lesser than or lesser than equal to. So here we can reformulate this, and then for the probability of x being smaller or equal to 20, we can insert this into cumulative density function. Here again, first we start standardizing this, so we go 20 minus the mean of 17 divided by 2, the standard deviation. So we get here a value of 1.5. This 1.5 we have to look up in the table. If we look this up in the table, here's the table, we go to row 1.5, that's the last row here. And then the second decimal is 0, so we stay with the first column, giving us here a value of 0.9332. So we have here 1 minus 0.9332, giving us a final result of 0.0668. Well, that's then all there is to this example and also to this course. So I hope you enjoyed listening to it. And if you're looking for additional exercises or additional units, feel free to visit the rest of the course or have a look at the corresponding playlist. I say goodbye and see you next time.